Hello, everyone. My name is Tilasi Malvagen. I'm one of the organizers of this virtual seminar series, this is actually the third event of this series, which is organized by the IFAC Technical Committee on Optimal Control. The first event was around 1 year ago. So as you can kind of see from the program of today, the way these seminars works is that we have a few talks dedicated to a topic related to control. And today in particular, the topic is trends in software and tools for optimal and predictive control. As I mentioned, this is organized by Tim and myself. Unfortunately, Tim is stuck in a train at the moment, but he will join us as soon as possible. Let me just come to the program here 1 second. So today's event in particular, we have three very excellent speakers with us. So Boris, Houska, Gionata, Cimini, and Paul Goulart. So I think we'll take a little bit of we will start at 5 past as the schedule tells us. So just before that, a few housekeeping rules, let's say. So this seminar is recorded. We will make it available online on YouTube shortly after today. So if you have any questions, so each of the talks has around 40 minutes, and then we have a few minutes of break in between the different talks. So there will be a chance to ask questions at the end of each talk. And if you have any questions, please write them in the Q&A tab. We will then read them out loud, and then we have an occasion to discuss. There will also be an occasion to discuss in general at the end a little bit as well. So I think that's it in terms of the introduction. So let's take a few minutes, and then in 2 minutes time, I will introduce our first speaker. So Boris, maybe meanwhile you want to start to share your screen.
Yeah, we'll try to do that.
I will stop to share mine. Okay, so our first speaker is Boris Houska. He's Associate Professor at the School of Information Science and Technology at ShanghaiTech University. He got his diploma in mathematics at the University of Heidelberg in 2007. He then got his PhD in electrical engineering from KU Leuven in 2011. He then spent some time between 2012 and 2013, very close to where I'm now, so at Imperial College, before he moved to ShanghaiTech University. His research interests include numerical optimization and optimal control, robust and global optimization, and fast model predictive control algorithms. And as you can tell from the title of his talk, today is going to talk about recent developments in the field of distributed optimization algorithms with applications to optimal and model predictive control. So Boris, without further ado, I'll let you take over.
Yeah, thank you to Lazi. Thank you for introducing me, and also thank you for inviting me to give this talk. I'm very honored to be part of this IFAC TC series today. So my talk will be about, as to Lazi said, distributed optimization and control with actually a new method called Aladdin. Well, it's actually not that new anymore. So actually my talk is divided into 3 parts. The first part will be about an introduction about what Aladdin is, and actually it is a distributed optimization method for non-convex optimization that we published in for the first time actually, or the first variant of which we published in 2016. So it's 5 to 6 years ago. And the first part of my talk will be about how this algorithm works, first of all, for those who don't know that yet. And then I will also talk a bit about what its advantages are in the context of non-convex optimization for large-scale systems. And I will talk about software and applications of it as well. So this will be an introduction, essentially, of my work from the past 5 years, I would say. And then the second part of the talk will be more about work in progress, actually, about an attempt, a very recent attempt to actually try Aladdin on a QP as a QP solver, so try to solve convex QPs with this distributed optimization method. I'll talk a bit about why we do that. Yeah, so actually the main motivation here will be to further scale up our software, and for that we would like to test our method on convex optimization problems. So I'll talk a little bit about that. And in the last part, if I have time, I will also talk a bit about applications of this method to real-time model predictive control. But let me jump right in. Yeah, so basically, I will try to keep the notation light for today. So I will talk about optimization problems which have a structure, actually. So we consider here just a simple equality constraint optimization problem, which has a separable objective. So these functions fi are potentially non-convex. So that's actually a challenge. And we have a linear equality constraint. Yeah, so basically we are saying that the sum over I over these ai xi's should be equal to b, where the xi's are block components of a large optimization variable x that we are trying to optimize. So essentially we're trying to solve a minimization problem, which may, however, be non-trivial in the sense that, first of all, that n could be very large. Yeah, so there could be a very large number of optimization variables. And then the other challenge is that these functions fi are potentially non-convex, and not even that. Yeah, so they might not even be differentiable in the worst case. So basically, it could be a rather general large-scale optimization problem that we are trying to solve here. And well, there are plenty of methods which can solve such optimization problems. Yeah, so this includes SQP method, yeah, so sequential quadratic programming methods, interior point methods, ADMM methods, also other distributed optimization methods like dual decomposition or gradient type methods, which could be applied here. But I will talk about a method that we published a few years ago, which is actually called Aladdin. And Aladdin actually stands for augmented Lagrangian-based alternating direction inexact Newton method. So it's a bit of a mouthful, but I will try to explain a little bit why we call it like that. So let me first explain maybe how this method works at all. So the idea is, yeah, so we have these xi's, which are optimization variables. They enter via these separable objectives. We try to start with initial guesses for these xi's. And we also choose an initial guess for the lambda, yeah, so for the dual of the linear equality constraint. And then we have some tuning parameters. I'll introduce them next. Yeah, and the method itself, it repeats by alternating between different steps. So the first step is actually an augmented Lagrangian minimization step. So here we are solving decoupled nonlinear programming problems, which are small scale in the sense that they only optimize over a block component of the overall optimization variables. But we are augmenting these separable objective functions fi with these terms like the lambda I transpose ia ya. So that's the Lagrangian term from the optimality condition, and then we augment this Lagrangian with this quadratic term. So that step in a way looks very similar to ADMM. Yeah, so basically very similar to the alternating direction method of multipliers. But actually, it continues. The algorithm Aladdin continues a little bit different from ADMM or other augmented Lagrangian methods, in the sense that what we do next is actually we compute, after solving this optimization problem, these decoupled optimization problems, we are computing a gradient or a subgradient of f. Yeah, so it could, if f is differentiable, this expression turns out to be the gradient at the optimal solution of that augmented minimization problem. And this is the gradient or subgradient of f, and then we optionally update these Hessian matrices Hi, which are approximations of the second order derivative of fi. Yeah? So now I've already just said that eventually fi is not even differentiable. Yeah, so it might also not be twice differentiable, but in that case, it's trying to guess somehow the curvature of that function, or trying to approximate this function somehow with something that looks curved. And after doing that, we do something. We do the next alternating direction, so to say, or the next direction in which we walk into, which is actually quite surprisingly a QP step. Yeah, so basically it's similar to sequential quadratic programming, that we are solving a quadratic equality constraint optimization problem in order to find the step direction delta y, and also a new multiplier lambda plus here. And what we do after this SQP step is we just update our variables x and lambda, and then we repeat this. Yeah, so basically, this is a method which alternates between solving augmented Lagrangian minimization problems. So it's basically an augmented Lagrangian step plus an SQP step, and we alternate between the two. Now let me talk a little bit about the properties of this method, so why we would be interested in looking into this. So first of all, there are a couple of special cases of this Aladdin method. Yeah, so essentially, if we make the rho, so this is the augmented Lagrangian parameter, if we make that very large, this means essentially that our first step, this augmented Lagrangian step, is redundant, which means that this whole method boils down to an SQP method. So essentially, we contain a sequential quadratic programming method as a special case. Then for penalty parameters, which are between 0 and infinity, and a very special choice of the Hessian matrices. So if we set the HI is equal to AI transpose II, then it actually turns out that we can show that this method is equivalent to ADMM, or at least one variant of ADMM, which is interesting. Yeah? So basically, this means first of all that that ADMM is contained as a special case, and then also it gives a suggestion why maybe ADMM is not the best you can do, especially if your function is differentiable or if you have second order information. Since here ADMM would amount to choosing a Hessian approximation that has not even something to do with the objectives fi. Yeah, so basically it's completely so this choice of hi, if we set it to AI transpose AI, this depends on the equality constraint matrices, but not on the objective actually. Yeah? So it doesn't give curvature information about the objective at all. But anyway, the other extreme case is that we set rho equal to 0, and in that case it turns out that Aladdin is equivalent to dual decomposition plus an inexact Newton step. So essentially, also the dual decomposition method is contained as a special case. Yeah. So from that perspective, the framework, or this alternating direction framework of Aladdin is very general and contains many methods, especially the second order methods from the SQP theory, and the first order methods like the augmented Lagrangian methods as a special case. Now, in terms of theory, yeah, so in terms of convergence theory, there's two types of results that one can establish. So one is that we assume that the functions fi is twice Lipschitz continuously differentiable actually, and that the minimizer is a regular KKT point. Yeah, so this is a standard assumption in optimization, and also we need that the Hessian matrices are not too negative. Yeah, so essentially they should. So the exact Hessian plus the HI should be, in this case, be positive, definite. In this case, we can show that the full step variant of Aladdin actually converges locally, either with quadratic convergence rate if we do essentially exact SQP steps, yeah, so with an exact Hessian approximation, or linearly if that approximation is sufficiently small. Yeah, but I mean this convergence result is interesting. It's a local convergence result, and the cool thing is that this works for general non-convex optimization problems. Yeah, so of course we don't find a global minimizer, but we are doing local optimization here. So it's so in a way the convergence theory is similar to SQP if you want to put it this way. But on the other hand, in contrast to SQP, we also have a global convergence result, and that holds true for the convex case. And this kind of exploits the similarity of Aladdin to ADMM. So here, the assumption set is quite different. So here we are saying that the FIs are convex, and the other assumptions are actually very mild. Yeah, so we assume a minimizer exists, and that well, here in this case, we assume that the scaling matrices are not updated, but that's just a technical assumption for now. And in this case, it can be shown that the Aladdin iterates actually converge globally to a minimizer, actually to the to the unique minimizer, or to real optimal solution. Since we have a convex optimization problem, there are no local solutions that are suboptimal. So basically, and this holds independent of the initialization. Yeah, so here the proof is very similar to ADMM essentially. So that's the other theoretical property that we can show about this this method. And now in terms of how this looks in practice, I think this an application reveals maybe the properties of Aladdin if we apply it to non-convex large-scale optimization problems. So here the problem that we tried in this case study was actually that we looked at a residential energy network, which has around 100 households connected. So actually that's a quite nonlinear model in the sense that many houses, batteries, solar panels are connected to that network here. We're trying to minimize the distance to a certain demand profile here and the cost of the operation also. So it's a large scale nonlinear optimization problem with which has important applications. And what we compared here in this right plot is actually, I forgot to put the axis labels. Yeah, so we are comparing the number of iterations versus the KKT residuum actually, and we are comparing three methods. Yeah, so we are comparing the ADMM methods, which are these red circles here. So here you see like ADMM here, in this case, you don't have a convergence guarantee actually, since this is a non-convex optimization problem, but it turns out that actually you can implement it. Yeah, so it works and it converges with linear rate, but actually quite slowly. Yeah, so we need many iterations. And we also compared to IP-opt, which implements an interior point method, and that's these yellow triangles here. So there the convergence rate is improved in the sense that interior point methods do use Hessian updates. Yeah, so here in this case we do have smooth objectives actually, but we do have also inequality constraints which are added. Yeah, and Aladdin outperforms these methods. Yeah, so basically it converges faster than these existing ADMM and interior point methods. At least that's something that we consistently observe for large-scale non-convex optimization problems which are structured. Yeah, and this residential energy network is not the only example where this happens actually. But also we tried other optimal power flow problems. So they are also from the energy system community. Or we also tried completely different applications in the context of vehicle coordination at traffic intersections. But actually, all of these papers you can summarize them basically by this plot here. So basically, what we managed to show is essentially that for all of these applications that we tried, we see that Aladdin has significant advantages compared to interior point methods, SQP methods, and also ADMM, in the sense that it contains also these methods to a certain extent a special case. Yeah, so we are trying to get the best of the worlds in a way by combining them into this alternating direction framework here. So that's why we are interested in this method. And now, in terms of recent developments, actually, so what we started to do, or actually not I started to do, but actually Alexander Engelmann, a student of Tim Faulwasser, one of my collaborators, started to do that. Yeah, so basically, we collaborated together and worked on a software called Aladdin Alpha, which is currently in a prototype phase of development, but actually already successfully implements Aladdin, the standard variant of Aladdin that I just showed. Yeah, so basically this works for large-scale optimal power flow problems. It can solve non-convex distributed optimization problems to local optimality. And we recently also, or Alexander uploaded this as a package as a MATLAB package, which is available for download. Yeah, so this is there's also a publication about this MATLAB toolbox recently in the OCAM, which just appeared in this year. But actually, one thing I wanted to talk about today is actually, so it's already saying here, so it's a prototype phase of development. So I would like to give a few pointers today, or discuss a few ideas of how to move on. Yeah. So basically, what we are trying to do is to get from this alpha stage software to more beta or more mature software, actually, for non-convex large-scale optimization. But this is actually a big step to take. Yeah. So basically, if you want to develop a software package or a more professional software package for optimization, this may be quite a bit of work. So we are trying to assess different ways on how to proceed towards developing such a software. And in terms of selected open problems that we are trying to look at is, so we are trying to look for ways to handle in a better way with linear and nonlinear inequalities. So what we currently see is that there are different ways to deal with these inequalities, in the sense that one thing you could do is, yeah, so here we have these separable objectives. So one thing you could do with an inequality is that we add these indicator functions to the objective, yeah, so which simply jump to infinity in case the inequality is infeasible, and just add this as a separable objective to Aladdin, which works so actually. Another option is, of course, to add inequalities to the SQP step. Yeah, so in the sense that also the SQP step could handle the inequalities. But then of course there's a question, which inequality do you move where? Yeah, so which one do you handle in the SQP phase? Which one do you handle in the augmented Lagrangian phase by projection onto the feasible set? So there are different ways to do that. It's not really clear to us yet on how to do this in an optimal way. There generally, for non-convex optimization, there are many parameters in the detail that are skipped now, which need to be tuned, and also an effective globalization routine is still missing. So this kind of problems were, for me, like the main motivation actually to try something first, in order to make software development maybe a bit more professional. Yeah, so to try to go from this alpha stage the development stage to a more professional software development. And basically the thing that we tried is to maybe say, okay, we are trying to attack a very difficult problem. Yeah, so we are trying to solve non-convex optimization problems to local optimality. Maybe what we can try first, if we really want to scale up to really large-scale optimization problems, we could try to solve a convex optimization problem first. Yeah, so just to, not in order to write yet another QP solver, but just to see how we compare, first of all, with existing QP solvers. And then also maybe to learn from that experience on how to tune all the parameters and all the details on so and how we make this and highly well performing code. So basically, what I'm trying to do in this work is actually I try to consider a large-scale quadratic programming problem, which has two separable terms in this case. So here we are just splitting the objective into two terms. So one is just a quadratic form, that's the f, which depends on this optimization variable y. And then, so we have here linear equality constraints, since this is the form in which we need it in the context of Aladdin. But of course, QPs have inequalities, which we now need to put into this other objective, which is essentially an indicator function. Yeah, so basically, here this g is 0 if set is, here we have a simple box constraint, and it's infinity otherwise. Yeah, so basically, it turns out that any quadratic programming problem can be written into this form, and Q and A are in this case sparse matrices. And of course, if we look at such QPs, yeah, so I said there are plenty of existing quadratic programming problem solvers which can deal with such QPs. So that includes QPA, so Mosaic, Ruby. Yeah, so those are they include, besides others, actually, QP methods based on these active set strategies. Then we have interior point methods implemented, for instance, in CVXGen, or it's the first order methods often based on this ADMM method. Yeah, so very recently we had OSQP is very well performing code for QP solvers. I'll also show that actually it performs really well on large scale optimization problems based on ADMM. But our goal here is actually, so I should say very clearly, our goal was not to develop yet another QP solver here, but actually in order to understand how Aladdin compares with these existing QP solvers. Yeah, so in a way, we contain many algorithms as a special case, so we wanted to understand what is it doing if we apply it to QP. And the other thing is that the other goal that we have here is we want to, if we want to develop a high performance non-convex optimization method, I said that, so basically it helps eventually to test on the convex problems first. So here's what happens if we tailor Aladdin to a QP. So basically the thing is, so those are the steps that I will show now are exactly the same as on the previous slide. So just here it's tailored for that particular situation. So I just repeat it because I think it's important to keep that in mind. So basically, recall the main steps are that we solve these decoupled augmented Lagrangian problems, which here boil down to solving, a quadratic minimization problem, which can be done by a sparse linear algebra solver. So basically this F is just a quadratic form, and this term here is quadratic too. So basically we are just minimizing a convex quadratic form. That's fine. So this is just a linear algebra problem. And the other problem, actually, the minimization over this indicator function G, turns out to be a projection problem. So basically, this step one is it looks I think familiar to many people in our audience actually who've tried to implement ADMM maybe. So where you have like of course these projections onto a box as well. So basically that's not surprising. So we do an augmented Lagrangian step here, which involves these operations. But now what we do next is actually, so we compute this gradient of the F and the subgradient of the G. That's fine. And then the interesting thing is that we do something that looks very similar to SQP. So here we differ again from the ADMM method. So which means we can update actually Hessian. So I put this a bit in quotation marks. So the Hessian H is fine. So we are trying to approximate the second order derivative of F. That's easy. We have that explicitly. But when we also need to choose something like a second order approximation of the second order derivative of that indicator function, which of course in this form does not exist. So we'll have to talk a bit about how to choose the K. And then we solve this equality constraint minimization problem, which is again a linear algebra problem. And after that, we update our variables and continue this Aladdin code. So basically, this is again these two main steps: the augmented Lagrangian step here and the equality constraint consensus QP, which amounts to an SQP step. Now, actually, the properties of this is actually what we saw is we tried it out. So we implemented it. It converges for LPs, QPs without regularity assumptions. So the only assumption is that those QPs need to be convex. Of course, the convergence rate is in general linear since G is non-smooth. So G is an indicator function. And then generally, this method behaves similar to ADMM in the sense that also infeasibility and unboundedness detection is similar to ADMM. But the difference to ADMM is that we have a similarity to SQP method. So we can update the Hessians. That's what I want to talk a little bit about next, actually. But actually, this Aladdin iteration, if you work it out, so it's neither equivalent to ADMM nor to SQP since it mixes both. And it can also be used as local solver for non-convex problems, of course. But I mean, that's now it's tailored for QP. So the Hessian for F is we don't have to talk about that. So basically we know that it's given as the QP data. But actually, if we want to get a Hessian update for the indicator function, what we can do is actually we can approximate this indicator function by a relaxed barrier function. So that's actually this idea is from interior point methods now. So we are blending this method with an interior point method. So basically we choose this, we introduce these log barriers. And now the idea is actually to update this Hessian approximation K from time to time at least by computing the second order derivative of these relaxed log barriers. So that's just a convex form on the feasible domain. Since we have a minus log here, and then we compute the second order derivative. It's a diagonal matrix which we can compute explicitly and implement the augmented Lagrangian and SQP step based on this on this interior point type of choice of Hessian approximation. And we do choose the relaxation parameter such that we always stay in the feasibility domain. So basically W was the projection of the current iterate onto the box, and this is our current iterate. So basically if we over relax a little bit by the infinity norm of that, we know that we always evaluate the log barrier at the point where the log is defined. So basically in the feasible domain of this log barrier function. And yeah, and this log barrier parameter is then just adjusted based on the current primal and dual residuum. So trying to make that barrier parameter smaller while our algorithm converges. All right, so that's how we choose that. And actually, what we saw was actually quite impressive. So here we tested that Aladdin method essentially with a sparse QP, which has more than 100,000 non-zero coefficients. So that's actually quite a serious size of QP. And actually, we are seeing again a convergence plot. Yeah, so basically what we see is that if we use constant matrices, if we use constant Hessian matrices, actually they do one scaling step at the beginning. So we scale them optimally based on our current initial guess, and then but then we keep the Hessian matrices constant. So what we see is, of course, a linear convergence rate. Yeah, so that's what we expect from Aladdin. And the active set is eventually detected after almost 7,000 iterations here. While if we do these log barrier Hessian updates here a few times, yeah, so basically at iterations 3, 9, I think 27 and 240 or something, we did, so there's some heuristic which tries to guess when it's a good time to update the Hessian matrix. It's expensive because we have to recompute the linear algebra decompositions. Yeah, but basically what we saw is that if we update very few times based on this log barrier, our algorithm converges much faster. So actually, it turns out that the second order information helps in order to speed up the code by orders of magnitude. Yeah. So here we detect the active set after around 700 iterations or so. And yeah, in terms of runtime, we were equally surprised actually. So here in this case, we tested the same QP, yeah, so with different existing QP solvers. So is that, yeah, so the idea was not to outperform these existing solvers or to claim that we are more stable or whatever. Yeah, so it's just like to get the order of magnitude in terms of the runtime right. But what we saw is actually that Aladdin was here able to solve this QP within 0.8 seconds. Yeah, so based on the prototype Julia code that we just used to implement this code that we had there, and then we also compared with Gurobi and OSQP, which have the same order of magnitude. So that's basically the order of magnitude that we wanted to reach here. So basically, in summary, what we can say is that we reach the same order of magnitude in terms of runtime for large-scale QPs. And we tested with different benchmarks actually, randomly generated benchmarks, MPC problems, also other benchmark collections. So where we pretty much consistently see that, this method seems to be performing extremely well also on QPs, which was very, encouraging for us to see somehow too, confirming that we want to develop this algorithm further next. Yeah, so that's basically the current status where I just got here. That's what I wanted to report on. But I will in the last part. I don't think I have much time left, but I will probably say a few words about the applications of this method in real-time model predictive control. So actually, one of the applications actually of Aladdin is, of course, that we can use it to solve large-scale MPC problems. They could be linear quadratic with the method that I just showed, but they could also be completely non-convex by using the previous method that I showed. Yeah, so it could be both type of benchmark MPC problems. But actually, one thing that makes it interesting is one thing or one strategy that we could try is, so if we have a model predictive controller with receding horizon, we can warm start the solver and only implement a finite number of these Ala-Italien iterations per sampling time. And actually, there's a whole theory behind it that I won't have time now to go into. But actually, it turns out that for linear systems, at least if we only have input constraints, we can give guarantees that this actually works, even if we have a finite number of iterations. So we did some stability analysis for that. But let me show how this performs in practice. Yeah, so here we tested that also in a case study with a mass spring damper system with around like 100 states, 50 controls, and quite long control horizon actually of 100. And what you're looking at is the suboptimality of the MPC controller compared to an exact MPC controller. Yeah, so basically J star is the optimal performance which you could get by implementing the MPC controller exactly. And this J infinity MPC is essentially the MPC control performance that we obtain by implementing only Imax iterations of Aladdin per sample. So so with incoming measurements basically, and so basically the suboptimality is relative. So basically this is crap. If you do only 3 iterations, you're 100% suboptimal. So obviously that's not what you would use. But actually, for instance, if we choose Imax equal 8, so if you take 8 Aladdin steps per sampling time, you would reach a very decent accuracy. So suboptimality is much below 1%, and we gain a factor of 100 in terms of runtime. So it's much faster than the exact MPC method. So and also here it turns out, in order to reduce the number of iterations per sampling time, actually it's very important to do these log barrier updates here for the linear quadratic case in order to make this work. I think this already brings me towards the end of my talk. I would like to use the remaining few minutes actually in order to summarize a few conclusions and maybe also give a few pointers of how to continue next. So what our outlook could be. So one of the things that I tried to convey today is actually that Aladdin is a distributed optimization method. So we published this method, as said, originally in 2016. It was meant to be a non-convex distributed optimization method, which combines ideas from different research fields. So essentially it combines sequential quadratic programming methods in the sense that Hessian updates are possible. That's also what I talked about today. It combines ideas from ADMM in the sense that it uses distributed augmented Lagrangian steps, and it also contains ideas from interior point methods. So we saw today that at least for QPs, these log barriers seem to be extremely effective for trying to guess the Hessian approximation of that iteration in order to speed up the convergence of Aladdin for convex QPs. So and what I tried to show today, and this is exciting news in a way. So I haven't even published this anywhere. It's really very recent actually. I just did these experiments a few weeks ago. So basically, but we saw that this prototype Aladdin-based QP solver is as fast as mature existing QP solvers actually, which looks very promising. So basically, what I have as an outlook is that I'm hoping that this Aladdin method can give us a unified perspective somehow on augmented Lagrangian SQP and interior point methods that, in my opinion, could help to develop the next generation of convex large-scale optimization methods, but then also software. So essentially, we want to make this step from this alpha stage software now to a more mature beta stage, or maybe even software that we really want to release later or could use in industrial applications as a convex or non-convex solver based on for large-scale optimization problems. So essentially, this is the perspective that I want to give here. And I mean, this is also, by the way, I have many co-authors that I work with on this. So I've been collaborating with this since a long time with a PhD student, Yuning Zhang, who's now at EPFL. I've collaborating with Tim Faulwasser and Alexander Engelmann, who were helping a lot in terms of writing this Aladdin Alpha software. But actually, this is also an invitation to anyone who is actually interested in currently developing convex or non-convex optimization methods for large-scale applications. So if you're interested, please get in touch with us. So we are very open for collaborating in this. Or I think we need a bigger team also for working on software if we want to make this really mature. Last but not least, I have a few references. So in case you want to get deeper into this, so the original publication on this is actually appeared in SciOpt. So that's the augmented Lagrangian-based algorithm for distributed non-convex optimization. So this Aladdin method, which I showed on the second slide already. And there's a few other publications which discuss variants. For example, this one is about a bi-level distributed variant of Aladdin, which can be applied to decentralized problems. And this TAC article here contains ideas on how to use Aladdin as a real-time MPC solver, while ensuring stability constraints. And very important also the last very recent publication on this, on our first steps towards developing a software based on Aladdin. Yeah, I would like to thank you for your attention, and I'm very open to take questions.
Thank you, Boris, for this very nice talk. So as I mentioned in the beginning, if you have any questions, please feel free to write them in the Q&A. I see that we actually have 2 questions already, so I will just read them out. So nice work and talk. I have 2 questions. What is the main difference between Aladdin and Ocado? And 2, is it possible to use Aladdin for Tube MPC?
Yeah, okay. Thanks a lot for both questions, actually. Aladdin is itself a distributed optimization method, which is, as such, is not directly tailored for optimal control problems. Yeah, but of course, optimal control problems can be written in the form of an optimization problem after discretization. And then you could use Aladdin on this in order to solve this optimization problem. Yeah, so basically, if you so Ocado was originally a software which I wrote 10 years back or so, which essentially converts non-convex optimal control problems by discretizing them with different methods and writing them as a nonlinear optimization problem, and then using SQP methods on top in order to solve the arising optimization problems. And this work on Aladdin now does really focus on the optimization part. So we are trying to scale up to even larger optimization problems. So we are having optimization problems with 1,000, 10,000, maybe even hundreds of thousands of optimization variables in mind. Yeah, so really large scale problems. And the actual challenge is that it's difficult to get a high convergence rate, first of all, and also to initialize the solver. So one of the key motivations here is really we want to look into Aladdin because it converges reliably from convex problems. Yeah, so I've showed this today for the QP part. And we hope that we can carry some of these ideas over to also make non-convex optimization more reliable. So that's really the goal here. And I think I have a similar answer to the tube MPC questions. Yeah, so basically tube MPC is a method for robust MPC. And of course you could, so as soon as you manage to reformulate your tube MPC problem as a large scale optimization problem, you could use Aladdin on this too in order to solve the optimization problems which arise there.
Perfect, thank you. So we have a couple of other questions as well. So the next one is the coupled QP step decomposable, or does it remain a central QP step?
Yeah, okay. So let me go into the QP step. Thanks for this question. Actually, I think this is again a very important question to ask. Actually, so I think the answer comes in 2 parts. Let me first talk about the QP solver part. So here we really have 2 steps. Yeah. So one step is this projection step. Yeah, so basically this is a decoupled step, which is a QP step in a sense, but it's an unconstrained QP. So this one is an unconstrained QP, and this one is a projection onto the box. So that's fine. But the actual challenges, and there you're right. Yeah, so we are solving a QP as part of a QP solver. Yeah, so which is kind of weird. But actually, the advantage of this QP here is that it is a centralized QP, unfortunately, in this form, but it has no inequality constraints. So basically, a sparse linear algebra solver can exploit the sparsity pattern of H, K, and A actually in order to solve the step with a linear algebra method. The other part is, of course, yeah, you're also there. It's interesting what we do with the QP in the general Aladdin variant for non-convex optimization. Also here we do a QP step. It is also based on an equality constraint QP, but there are indeed variants where we also it's also possible to augment this here and write inequality constraints here during the inequality step. Actually, that gives a different variant of Aladdin, and at the moment we don't know which variant works better. So in the numerical performance, we see there are some advantages of writing at least some of the inequalities here, but this makes the QP step a bit more expensive to implement. So we are not really sure yet what is the best method. So it's in a way an open question. Regarding the question whether this is centralized or decentralized, actually there's different variants here. So basically this one here is a centralized QP that you would have to solve in each iteration. That may or may not pay out, but there are other variants in this. So I jump back maybe to the to this paper on the bi-level distributed Aladdin. So this actually leads so by decentralizing all the equality constraint QP even once more, you end up with a decentralized version of Aladdin, which then scales up eventually even better. Yeah.
All right, thank you. So I think we have a couple more questions. I will take one of them, and then maybe the remaining ones, Boris, if you can answer them offline in the Q&A, that would be great. So there's one question here in the chat. So are all Aladdin iterates feasible in the QP case? Does this depend on the initialization? If they're infeasible, do you compute the suboptimality by looking at the cost?
Okay. The question is whether it's feasible or yeah. Okay. So basically for the QPs already, okay. So essentially this, of course the QP that you were solving could be infeasible. In that case, Aladdin would detect that, but actually I wrote this here, so that there's actually, so the infeasibility detection is very similar to ADMM actually. So what you're trying to look at is you're trying to show that the dual iterates kind of converge to a point, and then you get a dual certificate of infeasibility during the iteration. So I haven't put this here anywhere on the slide, unfortunately, but it's not very difficult to actually show that Aladdin also converges if the QP is infeasible, but then it converges to an infeasibility certificate, so to say. So that's in a nutshell what happens. I hope that answers the question now.
Perfect, thank you very much. So actually we still have 3 minutes. I think the next question is also not so long. So the question is, can Aladdin be used for mixed integer programming?
Oh, okay. Well, that's an interesting question. Yeah. So basically, yeah. So I mean, one thing is, so this Aladdin iteration is extremely general. Yeah. So basically, in principle, we are solving decoupled NLPs here. But one thing that we shouldn't forget is, of course, this method is meant for non-convex optimization, but it does converge to local minimizers. So if you do this on a mixed integer nonlinear optimization problem, this would mean that yeah, some of these optimization variables would be integer valued. No problem so far, but you would find a local solution, and whether you are happy with this in an integer context is of course a different question. Yeah? So usually in integer optimization, it is usually very important to deal rigorously with the integer part. So one variant actually that we published recently is a variant of yeah, actually distributed optimization for mixed integer problems, where actually instead of solving a QP in this step, actually you can solve a mixed integer LP or mixed integer QP. And in that case, it's possible to develop distributed optimization methods for mixed integer optimization, which unfortunately also only converge linearly. But for some applications, they work well in practice. So so the answer is yes and no. Yeah, so yes, you can use Aladdin on mixed integer optimization problems, but no, it will not find the global solution. Yeah, so it can be used as a heuristic.
Okay, perfect. Thank you very much. So again, Boris, thank you very much for the nice talk. So as I mentioned, it will be an occasion to discuss a bit generally at the end as well, but I think I will introduce our next speaker. So maybe Gionata, meanwhile, you can share your screen. Yeah, it's possible, Boris, that you have to stop sharing your screen for him to be able to do it. I'm not sure. Cool. Okay, so let me introduce our next speaker. So I already said it, but our next speaker is Gionata Cimini. So he is currently technical manager for numerical optimization at ODYS. He did his master's in computer and automation engineering in 2012. He then did his PhD degree in information engineering in 2017 at the University Polytechnica Dänemark. During this time, he was a guest PhD scholar at the IMT School for Advanced Studies in Lucca and a visiting PhD scholar at the University of Michigan. After completing his PhD, he was then research assistant at the information department at the University Politecnica Marche and at the Automotive Research Center at the University of Michigan. He has then been working for some time at General Motors company in the US before he joined ODYS in 2017. His research interests include model predictive control, embedded optimization, and in particular their applications to various systems in automation, aerospace, and power electronics. And as you can see, his talk today is going to be precisely on embedded optimization. So, Gionata, I'll let you take over.
Yeah, thank you for your kind introduction, and also thank you for the invite. It's really an honor to be here. Let me start by introduce the companies. With ODYS, we are a private SME that was founded in 2011 as a spin-off of IMT in Lucca. So we are based in Italy, and the mission of the company is to bring state-of-the-art research in advanced controls to industrial production. We have been so far successful in accomplish this task, and you can see on here these are two papers that we co-authored with General Motors, and we can say that as far as we know, this is the first known application of real-time MPC in high-volume automotive production. And today, we can say that our software for real-time embedded optimization in general, and more particularly MPC, so model predictive control, is currently running on more than 3 million vehicles worldwide. So we are quite proud about that. So this is the outline of my presentation. So I want to present you a list of software tools that we have developed with having in mind the target of embedded optimization, embedded model predictive control, and especially tailored for production. So we will start from quadratic programming in general. So we'll show you our solver, or this could be solver, and then we will move in the second part of the presentation to model predictive control, where I will tell you about some softwares for either linear time invariant MPC, generic MPC, and MPC based on deep learning. So let's start from quadratic optimization. So it goes without saying that quadratic optimization is a building block for many optimization-based controllers, identification methods, allocation methods. And our solver minimizes complex quadratic programming problems that are proposed in this form. So our quadratic objective function subject to equality constraints, generic inequality constraints, and bounds on optimization variables. So as I said, it has been specifically optimized for problems that can arise in real-time embedded optimization. And on the right, you see on the infographics that it supports many interfaces, among which MATLAB, Python, R, and of course C. To now, it's licensed. This software is licensed to many automotive OEMs and also Tier 1 suppliers. So this is a short list of the main feature of the solvers, which follow quite tightly what are the requirements of embedded optimization. So and especially embedded optimization that has a production target. So first of all, it has a beyond state-of-the-art speed of execution. So of course, being fast is mandatory. It implements a proprietary method for solving QP problems, and it's not only fast on average, but also in the worst case. So it has a quite predictable worst case. It's reliable, and it gives an accurate solution. So it's very accurate in terms of feasibility and optimalities, and is also in single precision, which is quite important and sometimes overlooked by other competitors, because many embedded applications run in single precision, so it's quite mandatory. And it gives a detailed diagnostics of the optimization outcome. And another very important aspect is memory. So ODYS QP solver has a very light memory allocation and operates only, this is obvious, but it operates only on static memory, so we can say it's malloc free. And as a last point, it's very quick and easy, the deployment, because it's basically written only in a pure ANSYS without any library, so there are no includes at all, and it supports MISRA standard. It's compliant with MISRA standard, which is very often used in automotive. So I put here a setup for benchmarking the solver against well-known solvers. As you know, commercial solvers do not always allow to publish results or to compare results. So we just picked a selection of open source solvers that you probably already known and were also presented before. So CVXOpt, OSQP, QP Oasis, QP Swift, which is probably the latest in the list, and the QuadProg from Python. So keep in mind, this is not the MathWorks QuadProg. And this selection of solvers include active set methods, interior point methods, and ADMM methods. And some of them are more suited for dense problems, others for sparse problems. And in this setup, I'm basically cycling on a series of QP problems randomly generated with dimensions that are typically found in embedded applications. So a number of variables that goes from 25 up to 225, generic constraints that are drawn in uniformly in this set, so from n up to 3n, equality constraints from 0 up to 15% of the number of variables, an Hessian condition number, which makes the problem more or less difficult to solve, up to 10 to the power of 6. All the optimization variables are bounded, and also a randomly selection of constraint active at optimum from 10% to 100% of the optimization variable, which makes also challenging or more or less challenging the problems. Two important aspects here that I want to underline. So the test is done, so first of all, is done on this board here, which is an ARM V8 at 1.4 gigahertz, and it's been has been done in Python, this comparison. And it's only in double precision because most, if not all, of these solvers do not have a single precision interface, which is something that could be very useful instead, especially when you don't want, for instance, to wait to go to seed code before understanding what is the impact in your controller when you switch from double precision to single precision. So it's quite handy to have, for instance, a MATLAB and a Python interface in single precision that will help you understand the impact of reduced arithmetic precision. And ODYS QP offer both interfaces. And also all problems in this list are feasible with linearly independent constraints and finite bounds, because otherwise some of the solvers in the list will just fail. So our solvers support all of these features. So this is the first setup for dense problems. So we are running this benchmark is on 2,500 QP problems. And on this slide, I'm showing you the optimality, the feasibility, and the success rate of all the solvers in the list. So the optimality is basically the error with respect to the real optimal solution. The feasibility is the largest constraint violation. And the success rate is either if the solver returned a fail or if the solution was completely out of place. Consider that for production, even a few fails, so these are very high percentages in general, but even very few fails could not be really acceptable sometimes, if not always. And the results that I'm showing here in the two pictures for optimality and feasibility are just for QPs that were solved successfully by the different solvers. So when they succeed, all the solver we can say that they are comparable. Obviously, first order methods suffers a little more, but we have quite good optimality and feasibility. What is interesting is the execution time. So if we compare the execution time, again, here I'm showing only problems where the solver succeeded, because maybe otherwise they can be very high, maybe the number of iteration or the time taken. So only problems where the solver succeeded. This time includes also the overhead of the Python interface, and it's acquired as on many repetition, like a shifted geometric mean of many repetition, 100 in particular. And in the figure, you can see the results for different dimensions, so from going to 25, 125, and 225. And in the table, there is a summary of what is the execution time. So on average, we can say that ODYS QP is 3.4 times faster than the best competitor, and 3.5 times faster than the best competitor. Of course, for each dimension, I took the best competitor with respect to that dimension. And then, okay, this was a dense setup, so problems where Asian and constraint matrix were dense, and this is instead a sparse setup. So the same dimensions as before, but here the Asian and the constraints have a sparsity of 80%. So 80% of the elements are zeros. And as far as optimality and feasibility go, we can see that the results are quite similar. So we have good optimality and feasibility. And again, most of the solver fail on some of the target problems. If we go to the time, it's interesting to see that, of course, sparse oriented solvers, like for instance QP Swift, are outperforming other solvers, while in the dense setup was the opposite. But still, our solver has a quite nice increased speed. So we have an average execution time that is 2.8 times faster, and a worst case execution time that is 2.5 times faster. So we are that's in line with also with what we have seen in dense for the dense setup. Then we move to, so we have talked about speed. So throughput is very important. It's crucial in embedded application because you want to be inside your sampling time, for instance, if you are running a control problem, so it's crucial. But memory sometimes, if not often, is even more important. First of all, because we are dealing with boards that have very scarce memory hardware, but also because sometimes the two concepts are coupled, because on some boards, so on some computational unit, moving around memory and accessing memory is very costly, which is something that sometimes it's not really addressed when we deal about the complexity of algorithms. So we often skip the part of allocating or accessing memory, but that on embedded part can really compromise the throughput. And it's also important to provide a quick memory feedback, which will help sizing the hardware or sizing the problem. So you want to know very well in advance in your design toolchain, you want to know if you are going out of memory. And many products do not support a really easy memory estimation because maybe they use external libraries. So with they might have numerous dependencies on themselves, or even worse, there is dynamic memory allocation, which is something that for embedded application for sure is not really allowed. So I have here also a memory benchmark for the solver. As I said, it's not super easy to get the memory occupation of the solvers solvers in general. So what I end up doing is just comparing against two solvers. One that is OSQP, that is a sparse solver, where the memory is computed by first generating the C code and then looking at the memory taken on the C code, and quadprog from Python, which has external memory allocation, so it's easy to infer the memory directly from the Python interface code. And here you can see on the left a dense setup, like I was showing for the execution rate, and where H and G are dense, so the Hessian and the constraint matrix are dense, but keep in mind that the presence of bounds also introduces some sparsity. And you can see that with ODYS QP solver, we take 2.2 times less memory than the closest competitor, which in this case, of course, I mean, not of course, because it's not really mandatory, but in this case, it's the dense competitor, so quadprog. On the sparse problems, instead, again, 80% of Hessian and constraint matrix is 0, so the elements are zeros. And also in this case, OSQP, which is a dense solver, outperforms, sorry, which is a sparse solver, outperforms the dense solver, but still with the ODYS solver, we are able to be 1.5 times less, more cheap in memory occupation. So we can say that I mean, the solver has quite low memory requirements, and it's also competitive on average sparse problems as well. And here a final slide about the solver, which I mean, tells some of the features that I'm not able to underline now for lack of time, but so basically it implements a scaling option, and we like to say that this is not a preconditioner like in many cases you will find. So it's not a problem solved on another space that is more well conditioned than the original one. It's a proprietary scaling algorithm that is performed on the fly depending on what are the solver steps. And then we have a complexity certification package together with the solver that is able to certify the execution time on some specific problems, like for instance parametric cookie problems. And this is very important because in embedded application, it's most of the time, if not always, is more important the worst case rather than the average case, the average speed. So knowing exactly what will be the worst case is something that is very, very valuable in embedded application because it can help you sizing the hardware properly or the problem properly. And this feature has been actually successfully applied to a multilinear MPC problem in production. And then it supports for many configuration of QP. So as you know, there are QPs with different properties. So for instance, parametric QP problems or time varying QP problems. And in these cases, we can either improve throughput or save the memory depending on specific problems that may arise in everyday optimization life. And then it implements a warm start to reduce the average execution time when a good optimal guess is available, of course. Then let's move to the second part of the presentation where we will talk about model predictive control. So very briefly, I don't think I have to introduce here model predictive control, but very briefly, the aim is to compute the optimal sequence of control moves over n steps by solving an optimization problem. So where you define a cost that reflects your control performance and your control effort. And prediction are made based on a prediction model of the system that predicts the future behavior of the process and subject to constraints on input states, outputs. And then once we have attained this optimal control sequence, we just take the first input and apply it to the system, move to the next time step, and do everything again from scratch, giving to the routine state feedback fashion. So, as you know, the QP that arise from model predictive control have a very specific structure that can be exploited by solvers. And this is what we do with this MPC version for our solver, which is called ODYS QP MPC. And it is a version of the solver. So it's the same solver, mathematically equivalent, but it's a version that is specifically dedicated to MPC problems. And why is that? So why we did this? To reduce memory occupancy and increase execution time. So exploiting the MPC structure for improving performance. And we can save on typical MPC configurations where you have constraints on inputs, outputs, input rates, and a prediction horizon that ranges from 10 to 30. We can, I mean, we have seen that you can save up to 50% of memory occupancy and reduce the time, the execution time, up to 50% as well. So these are quite nice results. And on this product, this dedicated MPC version is implemented in these two softwares for MPC that I'm going to describe you. So a linear time invariant MPC plugin and the embedded MPC toolbox. So let's start with the LTI MPC plugin. So this is basically a code generator for a linear time invariant MPC controller. So what is a LTI MPC is just MPC where the model is linear and the matrices do not change in time. So the idea here is that you can design the controller offline with, for instance, MATLAB model predictive control toolbox. And because a lot of people are very familiar with this toolbox, and so the idea is here to rapidly test the product without the effort of learning a new software tool. So you can just design your LTI MPC problem with MATLAB toolbox and then convert it to our framework that exploits all this QP MPC solver. Of course, it implements both the Kalman filter and the optimizer, both of them optimally tailored for dealing with MPC problems, of course. And both of them have been coded with all the requirements of embedded optimization in mind that I'm not going to repeat here. So this is the general workflow that you would use for testing and for implementing an LTI MPC controller with our toolbox. So you can design the toolbox very briefly. Then you just with one line of code, you can convert an MPC object designed with MATLAB control toolbox, MPC toolbox, to our framework, which generates a series of C and H files that implement both the Kalman filter and the optimizer, and the complementary block for Simulink, either software in the loop or processor in the loop verification, code generation, code deployment, everything that you may want to do with the Simulink block that support embedded coder. And this is what we did here, just to test out the product and to show you some results, which are propedeutic to show you what are the performance of this model predictive control MPC version of the solver. So it supports, of course, a processor in the loop, and that is what we did on this platform. which is a Texas Instruments C2000 microcontroller with 200 megahertz clock speed. So it's a real embedded board that is actually designed and commonly used for motion control, so for drives or converters. And we tried, again, the execution profiling in a processor in the loop structure. And given that, I mean, the processor itself is designed for motion control, we tried that first on a motor control problem. So the idea here is to show you three different examples. One that is small scale, one that is medium scale, and another one that focus more on robustness. So the objective, I'm not going too much into details because they are not important for the sake of the presentation, but basically we are in a field-oriented control strategy for a permanent magnet synchronous motor, where we want to control our stator voltages in the direct equator frame in order to have the currents in direct equator frame following set points that are provided by an external loop, which has the intent of controlling either the speed or the position of the motor itself. Why this is interesting? Because this type of controllers always run, first of all, on chip boards and at very high frequency. So we are talking about 10 to 100 kilohertz domains. And the constraints, given that we are in this DQ frame, are quadratic. So if you want to have a fine constraints and linearize, maybe with a polyhedral set like this, you may end up with numerous constraints. So this is the setup of this processor in the loop simulation, where I mean, we have just a linearization point regarding this. So it's a linear model, but it's been linearized around a specific shaft speed. And the objective is to track a specific pattern in the speed with many steps and also some disturbances in the torque load, while preserving constraints on the currents, basically, and on the voltages. The sampling time here is 0.3 milliseconds, so it's pretty fast. It has to run in a very short time, the controller, and the prediction and control horizon is 2 steps. So the idea here is to compare on this board, so on this 200 megahertz board, the results that we get in processor in the loop, both with MPC toolbox from MATLAB and with our ODYS LTI MPC. So the problem ends up being an optimization problem with 5 optimization variables and 26 constraints. And as you can see from the table, I'm comparing the maximum execution time, average time, memory occupancy in single precision, and the error in the optimizer. I have to say here, I forgot, this is a single, of course, I mean, this board runs just in single precision. So it's everything runs, all the optimization and the Kalman filter run in single precision. And as far as the performance, we can see that we are able to be 7 times faster than MATLAB MPC toolbox and 2.8 times less memory, which is quite a nice improvement. And also the error in the final solution, given that we are in single precision, is quite small and much smaller than what we get from MATLAB toolbox, which implements actually an active set method that is actually supposed to be also precise. So anyway, the most important message here is that with this tool, we are able to fit in the 0.3 millisecond processor task by sparing also some time, while this would be impossible with other solutions. Then let's move to a medium scale problem. So this is a demo from the MATLAB toolbox library. So it's much larger control problem with constraints. So it's a thermomechanical parting process, first of all, with 6 observed variables and 5 manipulated variables. The objective here is to regulate the energy applied to the pulp and the consistencies of the pulp in two different spots in the production unit, while maintaining vibration levels below a certain critical level in order to prevent these plates to crash, and also limit also the consistency to prevent the blow line plugging and damage in the fibers. And this is quite complex dynamics. It has many manipulated variables, many states, 7 states, and require long prediction and control horizon. And has constraints on both input rates, and outputs. This is what is going on in this simulation. So there are many things. I'm not going to touch them all, but very simply. So the sampling time is 0.5 seconds, prediction horizon is 20, and control horizon is 7. And I mean, on the right, you can see the measured variables. On the left, the manipulated variables. Motor load and consistencies are well following their respective set points, and constraints on vibrations and plates gap, dilution flow are respected. And you can see that the solver has to do many things here, because I mean, many constraints are active, so it's quite a challenging problem. And the QP size is also considerably large, at least for what is the typical dimension of embedded problems. So we are dealing with 36 optimization variables and 265 constraints. And given that the problem is larger, the QP solver has to do more things, the benefits are even more. So you can see that we are 27 times faster than MATLAB MPC Toolbox, and the memory saving is 3.2 times less. The quality of the solution for this problem probably is better conditioned. Is basically equivalent, just 1 order of magnitude less for MATLAB Toolbox, but anyway, that's fine. The one thing that I forgot, but probably was clear. Of course, the memory and throughput numbers that I'm showing on all these slides include both the optimizer and the Kalman filter, so the whole MPC routine. And then a final example, on which I want to target the robustness aspect of QP solvers and MPC routines. So it's the control of an aircraft, the attack and pitch angle of an aircraft, which is quite well known in the MPC community, because first of all, it's a demo from MATLAB, and then has the feature of having an unstable pole. So the linearized model has an unstable pole and saturated actuators. And so it's often used as a mean to underline the benefit of MPC over traditional controller, because you can deal very well with like situation like this one, like an unstable pole and saturated actuator, which can lead to instability for standard control algorithms like PID or. But this is true only if the mathematical machinery that is behind MPC is robust, because otherwise you can go into problems quite easily, even with MPC. So let's look at this problem. These are results in double precision. So we have a control horizon of 2 steps and a prediction horizon of 10, and constraints on the outputs for all the steps. On the left, you have the results with the MATLAB Toolbox. On the right, with ODYS MPC, and you can see that they are quite similar. I mean, nothing really changes. But when you move to single precision, you can see that problems may arise. So in this case, the condition number of deviation is 10 to the power 7, which is large, but not dramatic. And of course, numerical problems are even more amplified in a system like this, which is unstable. So you get basically closed loop instability if the QP solver is not reliable in single precision. And keep in mind that numerical problems can arise for different reasons. So also for weight scaling or unstable linearization, for instance. And then let's move to the last topic, which is ODYS embedded MPC. That is our toolbox for dealing with very generic MPC problems. So before I showed just a linear time invariant MPC problem, which is a very small category, so a very small subset of MPC problems. And with our toolbox instead, it's a very generic toolbox. It's a software library for implementing modulated control in real-time applications in general. It provides both MPC function and state estimation function, with of course an emphasis on everything that I have already stated. So execution speed, numerical robustness, limited memory footprint, and of course it's completely written in C code with no dependencies, MISRA compliant, no dynamic allocation, and I mean, things that we have already heard. So what is the key feature besides, I mean, being tailored for embedded application? The main feature is that is very generic and very, very flexible. So it's based on a rather general linear time varying and nonlinear prediction model. It supports advanced MPC features, like for instance, changing everything in prediction, so both model, constraint, blocking pattern, different blocking pattern for different inputs. So many really, really flexible. And the design specification can be provided both in C code and in MATLAB code. And it also support automatic integration, discretization, and differentiation for the prediction model. And it can also handle quite effectively the sparsity that may arise in the prediction model. You see here on the right some picture taken from a performance assessment tool that it is complementary to the embedded MPC toolbox for adding a detailed analysis of the MPC results. And here I'm showing you a very quick example, again taken from the library from MATLAB MPC toolbox. So it's an obstacle avoidance setup with linear parameter varying MPC. So where by LPD, of course, we mean that the matrices of the model are changed at each time step, but not in the horizon. And here the objective is to follow a reference velocity and avoid obstacle in the lane using adaptive MPC. So the prediction horizon is 25, the control horizon is 5, and we have constraint on both the distance from the obstacle and input rates. So you can see here on the left, I mean, maybe you are familiar with this now, but let me just explain it. On the left, we have our ego car, and this red here is the obstacle. And you can see this purple line here that is the constraint, and the vehicle trajectory that ends up being this yellow line. So the vehicle model is nonlinear, and it's here in the box. Is a very simple, I mean, it's a very simple demo. And this ends up being a QP with 11 optimization variables and 98 constraints. And here is the some benchmark results against MATLAB 2021 MPC toolbox. So the same that we were seeing before, but this time with the adaptive MPC block. So in this case, as you can see, we are 28 times faster on average. And 43 times faster in the worst case by saving a factor of 10 in memory. So quite a nice improvement. Just one quick thing: this timing here is not. I mean, it's just collected on a laptop. So here I'm showing just a very quick example of a linear parameter varying MPC. But of course, as I said, the toolbox support the linear time varying MPC and even nonlinear MPC. And for that, I have a few slides at the end of my presentation. So the idea here is, okay, let's talk about nonlinear MPC. And so nonlinear MPC is a kind of MPC where you use a nonlinear model of the process to make prediction and optimize the closed-loop behavior. So this means that we have to have at hand a nonlinear model, but nonlinear model, when they are physics-based, sometimes, if not often, they are very complex. And so an idea could be to leverage the very recent advantages in deep learning to substitute, even partially, the physics-based model with, for instance, a neural network that has been trained on data collected from the process. This can be a quite handy tool that can speed up the MPC design by a lot, because a lot of time could be spent on physics-based nonlinear models where they are very complex. And another advantage is that we can learn directly in this way the discrete time model of the system, and it's just a one-shot model learning. So you provide the collected data and that's it. Otherwise, you may have to go to like defining linear operating ranges and so on. So what we offer on this side here is this tool that is basically a plugin for ODYS embedded MPC that is called ODYS Deep Learning, that is available both in MATLAB and in Python, and it makes it easy. So once you have your neural network that you have designed with your machine learning library that can be PyTorch or Keras or TensorFlow, it makes it easy to generate, because it has an automatic generation of the C code of the neural network, to include this neural network model as our prediction model for MPC, and also the Jacobians for the MPC setup. It also offers some, of course, you can train the network as with your favorite tool, but it also offers efficient proprietary algorithms for training the small, deep feed-forward neural networks, which are typical in embedded MPC. So we usually don't deal with huge neural networks as prediction models for embedded MPC. And you can see on the right some benchmark against training done in Keras, for instance. And this also supports online learning, so supporting adaptive nonlinear MPC. I have here at the end just a quick example of where we have successfully applied this deep MPC, let's say, to an autonomous driving problem, where we want to manipulate the throttle and the steering angle of a vehicle subject to a specific drive policy. For instance, here on the picture in the right, we want to overtake an obstacle at first and then follow a second one from a safety distance. And in this case, we know that wheel dynamics are very fast and tire-rod interaction can be very hard to model. So the idea here is why don't we just use a black block model for vehicle body and wheel dynamics and a white box model for the vehicle pose. So ending up basically with a gray box model for our nonlinear MPC. And that this successfully applied in this example, and the workflow for doing this is very simple with this tool. So you just collect data and train and generate the C code of the network and the Jacobians of the network for being ready to be used by ODYS and by the MPC, and then you deploy the controller. So with a user intervention that is very minimal. So I think this concludes my my presentation. So thanks. So I hope this was interesting, and I'm open to questions, of course. And thank you for your attention.
Thank you, Gionata, for this talk. It was very interesting. It's also very nice. It must be very satisfying to know that you have made a solver and also that is running on 3 million vehicles around the globe. So there are quite a few questions in the Q&A, but just in the interest of staying on schedule, maybe you can answer those offline if that's okay with you. And then I think, Tim, maybe you can introduce the next speaker. But first, thank you again, Gionata. It was a very, very nice talk. Thank you.
Thanks.
It's my pleasure to introduce and to welcome Paul Goulart, who's joining us from the University of Oxford, where since 2014, he's an associate professor in engineering science and a tutorial fellow in engineering science as well. Paul has an astonishing CV where he has started off with a bachelor's and master's at MIT, then worked for the Harvard-Smithsonian Center for Astrophysics before he came back to control, did a postdoc at ETH, and currently his main research interests are high-speed optimization and control for embedded systems, data-driven and robust optimization, and machine learning. And Paul, we are very much looking forward to your talk.
Okay, thank you. You can hear me okay? Great, okay. Well, so thanks very much for the nice introduction, and thank you all for coming to my talk. And what I'm going to do is I'm going to tell you about some of the work that we've been doing here in Oxford over the last 4 or 5 years, I would say, on developing free and open source software tools for convex optimization. And I'm going to concentrate on the ones that we've worked on that use something called operator splitting methods. So I'll just start with the sort of obligatory first slide where I try to convince you that you should care about optimization. Convex optimization appears in lots of different applications, both in control, which I guess most of the people here are interested in, but then also in all kinds of other places like mathematical finance, machine learning, networks, and so on. And it can appear either as a problem directly. You directly have a convex optimization problem, which would be the top half of the slide, or it appears as a kind of sub-problem in an otherwise non-convex context. So we do things like Bayesian optimization or fluid problems, logistics, combinatorial optimization, switch systems, and so on. And all the things on the right are just applications that just I've happened to work on. I'm not saying that these are the most important applications. But you can see that there's a big range of different applications there of all different scales, all different speeds, all different sizes. And so it's worth trying to come up with nice generalized tools that solve these problems for us in a kind of flexible and accessible way. So what I'm going to do throughout the talk is to concentrate on this problem form, where I have at the top here, I have my minimization problem. So minimize some quadratic function with a possibly zero quadratic term and a linear term. And then I have some constraint that a times x has to live inside some set. And depending on the details of this problem, I get different problem forms. So if I were to take C to be a box, then this problem would be a quadratic program. If I were to take C to be a box and P to be 0, then the problem would be a linear program. And if I were to take C to be, say, the semi-definite cone, then I would have a semi-definite program. And so, there's a huge variety of problems that can be cast like this. And, you might see your problem in a slightly different form than that, even if it's still an LP. But you can always rearrange it, add variables, whatever, and get it down into this form. And so what I think we want to do is we want to come up with a general way of solving this kind of problem that's fast, that's embeddable, because we want to do it in real time on control systems, and that's scalable. And so I want to show you how to do this efficiently and in a way that works even on really low-level hardware, but also that works at really large scale. So we're kind of particularly interested in really small problems or really big ones. and the ones in the middle, maybe not so much. And so I'm going to try to show you that I can do both extremes using the same method. Okay, so that method is called an operator splitting method. And what I'm going to do is I'm just going to sort of sketch for you the basic idea, and then I'll try to put that problem statement into the terms that I've sketched out. So let's just suppose initially that I have a problem where I want to minimize the sum of two things. So I have these two functions f and g, and suppose f and g are both convex, but I don't know really anything else about them initially, other than to say that they could even be indicator functions of some set. And so if I wanted to turn a QP into this problem, I might take f to be the objective and then g to be the indicator function of the constraints. And often what happens is that the two functions are individually nice. It's easy to minimize a quadratic function, but when I add them together, it's hard. And so what I want to do is I want to split it into two pieces. So what I can do is, I'm going to start off by making the problem look a lot worse. And I'm going to do that by adding a bunch of variables, w tilde. So I've made this copy of w, and I have this equality constraint, so they're really the same thing. And then I've added this seemingly unnecessary term here at the right, which says that I want to add also the square of the difference between the two things. But by the way, the two things are equal anyway, so this doesn't seem to do anything. And it doesn't do anything. It doesn't change the answer. Any solution to this problem is a solution to that one. Okay, it's still bad because I can't minimize the sum of these two things easily. So maybe I could solve the dual. That's always a good trick. Let's try that. What would happen? So I would take those constraints that I just added and I stick them into my objective, so now they're gone again. And I tried to maximize over some multiplier the value of this Lagrangian function at the bottom here. And this is, again, not obviously any easier than what I started with, but maybe I can make some progress with this because now it's a maximization problem of an unconstrained thing. Okay, so that's my basic approach. Just make things worse. See if I can make it a bit better now. So if I were to solve the problem sort of directly by solving the dual, then what would I do? I would take this inner problem, I'd fix some w and w tilde, and I'd minimize. And then I'd try to find the gradient. And the gradient would just be the difference between w and w tilde there. So gradient descent on the dual problem would look like this. Minimize this function here, which is really just this one rewritten. Minimize that over w and w tilde, and then just go uphill for the multipliers. And just do that over and over again. And this is not a good idea because I still have this problem that the two things are coupled. So I have minimize a sum of these two functions, and I said that the problem is that the two functions are hard to minimize jointly. Okay, so what if I just sort of approximate the gradient? What if I were to take this problem, and instead of minimizing jointly over w and w tilde, I did it this way. First I fix w, and I minimize over w tilde, and then I take the new w tilde and I plug it in, and then I minimize over w. And now I have almost the minimum of this problem up here. I've just done it in 2 steps. And then I say, well, that's pretty close to the gradient. I'll follow the gradient uphill. And this is called an operator splitting method because what I've done is I've split my problem into first a problem where I'm minimizing over f, and then a problem where I'm minimizing over g. And now the utility of this square term is clear because if f is, say, a linear function, then this minimization won't be unbounded below. So each of these will have a nice answer, and I just do that. And that is basically the ADMM method. And so I can say lots of things about how this converges and so on. I'm not going to do any of that. Instead, I'm going to show you how to apply that to this problem. And I've immediately rewritten it so I have this extra variable z here. I say ax is equal to z, and z has to be in the set. And most ADMM-based methods would stop there. They say, I've broken it into 2 pieces. I'm instead going to do it in a slightly different way. I'm going to make even more copies, even more variables, and I'm going to say that x and z is one set of variables, which are in the constraints, and then the tilde ones are inside this equality constraint and then also in the objective. And let me see if I can turn that into a nice problem. So the first thing to do is to put those constraints into the objective function. I do that by making an indicator function for each one. And so now I have, more or less the same thing as before. Now I'm going to add a quadratic term for the difference between x and x tilde and z tilde. And now what's happened is that I have my problem exactly in the form that I want. This is f, minimize a quadratic, subject to this equality constraint, and g is just the indicator function of all the other constraints. And so if I put that into my ADMM algorithm, then I get something that looks like this. I minimize over this quadratic function. I have still an equality constraint there because I kept the indicator function with f. And I'm going to minimize that. Okay. And then I'm going to minimize over the g part, which was my constraints, but minimizing a quadratic function subject to an indicator function of a convex set or a cone, say, is just a projection. So I project onto the set. And so my whole algorithm boils down to 3 steps. It's 3 lines of code, really. Minimize a quadratic function subject to an equality, project onto a set, vector addition and multiply, and just do that over and over again until it converges. And there's lots of things to be said about all of these steps, and I'm just going to address the first 2. So if I'm solving a quadratic program, then the main problem, the main difficulty, the main computational cost comes in this step right here, which is minimize this equality constrained QP. And that's at least easier than an inequality constrained QP because I can just solve it by writing down the KKT conditions for this problem. So if I look at only that first step, the problem is minimize a quadratic subject to an equality constraint. And so if I just write down the KKT conditions for it and solve, then it turns out that you can solve this problem just by solving a linear system of equations. And okay, I've eliminated a few variables, but it boils down to solving this thing here. And so the main computational cost for a QP is to just solve this system over and over again. That's the first step, which is the linear solve part. And now you can see that the splitting that I did, where I added the extra variables and then I added even more extra variables, the reason for that becomes now clear because this system on the left is really nicely structured. So if P is maybe 0 because I have a linear program, the upper left is still positive definite because of the sigma term. The bottom right is still negative definite. And so the whole thing is what's called a quasi-definite matrix, and it's always solvable, regardless of the problem data that someone gives me. And this is really important in applications because people give you all kinds of sort of garbage problem data. A might have 0 rows in it. There might be repeated rows, might be weird scaling. And I'm certain that I can always solve this system because it's always definitely full rank. And it also has this, because it has this quasi-definiteness property, it's LDL transpose factorizable. So I can always tell you exactly what the non-zero pattern of the factors of that matrix will be, even without knowing what the problem data is. And then the other thing to say is that in my algorithm, I need to solve this system of equations over and over again, but the left-hand side doesn't change. So I factor this thing one time, and I just remember the factors, and then every iteration is just a forward and backward substitution on the factors. So I said that this is the direct method. I could also solve this with an indirect method if I want, but the main idea is that this thing is always solvable. So that's my first step. That's where all the computation cost goes when I solve a QP using this method. There's many things more that could be said, but instead I want to show you software that's available to you to do this. So we spent a long time trying to make a nice software package for this. And we did that by releasing this package called OSQP, which we did, I guess, about 3 years ago, say. And it's all open source. It's written in C. It's pretty fast. And we put a lot of work into making it accessible. So it has lots of interfaces to other languages because most people don't want to directly write their problem in C. So in any of the languages here, you can install it with, I think, at most 2 commands. And it's only 2 because MATLAB is sort of annoying. It needs 2 commands. In the other ones, you can do it in 1 command. Python, you just pip install OSQP and it just works. And it's really important that we wanted to make it just work. And it also works through all the kind of common interfaces that people expect. So it works through CBXPy, it works through JUMP, it works through YALMIP, it works through, what's the other one? CVX in MATLAB and so on. So you have lots of choices and it's just easy and it just works. That's the main idea. And we have especially this code generation feature. So what you can do, for example, if you're working in Python, is you can define your Python problem. You make this solver object, maybe you're doing some simulations or something, then you're happy with it. So then you create your problem there by just defining the problem data. And then you just say code gen, and it just dumps a solver for you with all of the matrices pre-constructed, statically allocated for you into a folder. And then you can compile it directly onto your embedded system of choice. And then you can deploy it to your system. And you can, there's some amount of configurability there. If you want it to be completely statically allocated, you can do that. If you want to allow free refactorizations, you can do that. If you want to allow updates to the problem data, you can do that. And it just works. And so this has got a lot of users. We have something like 15 million downloads of this software now. And I would like to say that that's because it's really fast. It is really fast. I think it's mostly because it's free. Okay, so that's the QP situation. But now if I want to solve an SDP, then, and I want to use the same method, the situation is a little bit different because I'm going to go back to my my algorithm description, and I want to consider what is the hard part of this algorithm now. So in a semi-definite program, your constraint here is that C should be a semi-definite matrix. And so this bit is now easy, or relatively easy. Solve this QP. That's usually pretty fast in a semi-definite program. But the hard part is to project onto that set, to project onto the semi-definite cone. That's where all of the computation time goes in a semi-definite program. So it's worth asking why. So in the QP case, what happens is that if I were to take my my quadratic program constraints to be a box or a set of linear inequalities, say even just one-sided, then projecting onto the box is easy. I just round. So if I have a point V here and I want to project onto the box, then I just do max min of the left and right-hand sides of my bracketing inequalities, and that scales linearly with the vector size. I could even parallelize it, then it would be even faster. And so the QP situation, that second step is basically free compared to the linear solve step, and probably 90% of the time goes into the linear solve. But for a semi-definite program, it's a different situation because the projection is not so easy anymore. So let's look at what the projection looks like. So for a semi-definite program, I have some variable. It will be a matrix valued variable. And I want to project it onto the positive semi-definite cone. So how should I do that? So what I do is I take my variable, call it V, some matrix, and I do a matrix factorization and eigenvalue decomposition on it. And I get U lambda U transpose. And then the semi-definite cone is the set of matrices that have non-negative eigenvalues, but lambda might have some negative eigenvalues. So what I do is I just zero out all the negative ones. And it turns out that if I zero out all the negative ones and I put my matrix back together, then that is the projection onto the semi-definite cone. But this is not a nice operation because I have to factor, that's a cubic operation, and then I have to remultiply everything back together, which is also expensive. And so the projection cost now scales with the cube of the matrix size, and so that's why all the time goes into the projection part. And this is a problem because in a lot of control problems, especially, particularly things like network analysis or sum of squares problems, the size of the problem can be really huge. You might have hundreds of thousands of variables even, and you don't want to try to factor a 100,000 element matrix. So, and bearing in mind that I have to do this every time, every iteration, I have to make this projection. So we've spent a lot of time working on this problem, and I'll just show you one of the things that we did, which was a way of trying to do what's called chordal decomposition to break the problem down into smaller pieces so that the projection step can be accelerated. So to do that, I need to tell you a bit about chordal graphs and show you the connection to a sparse matrix. So if I have a graph is a set of nodes, V, so I have nodes 1, 2, 3, 4, and a set of edges that connect them. And so the composition of the nodes and the edges gives me a graph. And I say that my graph is chordal if there aren't any sort of four-sided cells with nothing that goes across the middle. So this one's not chordal. It doesn't have a chord or a cross link, whereas this one is chordal. And if it's not chordal, I can always stick in some terms. So the definition is the graph is chordal if every cycle of length 4 has a chord. So what does this have to do with optimization? Well, so the first thing I can say is that if I have one of these chordal graphs, then there are methods called clique decomposition methods that take the graph and they break them up into what are called the maximal cliques. You can think of a clique as being a fully interacting subset of the nodes. And so I have these methods where I take this graph and I break it up into all of these little pieces. And I want to use this idea to turn my big semi-definite program into one with lots of smaller pieces instead. Okay, so to do that, we have to connect it up, first of all, to the optimization problem that we're solving. So a matrix, we can think of a matrix as being connected in some way to a graph. I have a matrix with a bunch of 0 and non-zero elements. I call the rows and columns the nodes, and everywhere where there's a possibility of a non-zero, I make an edge. And so now what I can do is I can do chordal decomposition on this thing, and it corresponds to the dense bricks in my matrix on the left-hand side. So let me just show you, there's my cliques. So you see that 1, 2, and 6, they are all fully interacting with each other, and 1, 2, and 6 form a dense subset of the rows and columns. If I would eliminate rows and columns 3, 4, and 5, I would have a dense brick, which corresponds to a fully interacting clique. And I can do that for all of the other cliques. And so I get these 3 different pieces. And I don't have to have the one in the middle. As long as I've covered every node is in some clique, then that's enough. Okay, great. So what? So why it's useful is because of this really very nice theorem that says that this whole matrix is positive semi-definite if and only if you can break it up into a sum of matrices defined on these cliques where each one of the m's is itself positive semi-definite. So there's different ways of doing it. I can allocate, x22, I can put different amounts of it in the green one or the blue one. But if I can figure out a way of doing that so that green, blue, and red are all semi-definite, then I'm sure that the whole matrix is semi-definite. And this is nice because this matrix is big and green, blue, and red are all small. And so I can take this as an equality constraint, and now I have some conditions on these submatrices. Okay, so that's not our idea. That's a sort of common idea. What I want to show you is that that's not necessarily always the best thing to do. So we have this idea called clique merging, where sometimes I want to put some of the blocks back together, because what I want to do is I want to maximize the rate at which I can factor all of these little blocks. So sometimes it's better to combine. When is it better to combine? If I have a problem with lots of little blocks with a small degree of overlap, then you can kind of see that factoring this great big matrix would be worse than factoring all of these little ones one after another, especially bearing in mind that I can do the little ones even in parallel. So here, multiple blocks would be better to factor. Whereas on the right-hand side, I've got 2 huge blocks that almost completely overlap. There's just this one little piece missing. So maybe it would be better to factor the whole thing, which is size n, rather than factor 2 things, size n minus 1. And it would be a lot faster. So here, one big block is better. So how can I tell when I should merge things together and which things am I allowed to merge? So, okay, so what we do is we use what's called the clique tree. And most methods that do clique merging, they operate like this. They have their matrix sparsity pattern. They have some chordal graph that goes with it. And here I have these big circles here. These represent fully interacting subsets of the rows and columns. So here I have VC. This is some great big dense block. And so in my chordal graph, I have this fully connected sub graph VC. So if I were to find the cliques, what would that look like? So I would start with just find any clique, the yellow one, say. And so you can see that if I eliminate this row and this column, then I would have a fully interacting dense yellow block. And that corresponds to this clique here. And so I write that down over here. That's one of my cliques. And then I go looking for other ones. There's a green one. And that's a different clique. And I'm starting to assemble on the left-hand side this thing called the clique tree. And I do that over and over again. There's the red one. Okay, and there's the blue one, and that covers everything. So how could I go about merging? Well, this kind of standard method is that people form this clique tree, and then they just merge by sort of looking at the clique tree. So in this clique tree, you can see that I have the red and the green are parent-child. That would be a valid merge. You'd be allowed to do that. And the green and the blue, they're siblings. That's also a valid merge. You could put those two things together. And they have some kind of heuristic that decides when to do this. But the problem is that the right thing to do in this example is to merge that corner right there, because I have two big blocks that are almost completely overlapping. And the problem is that the red one and the blue one, they're neither parent-child nor sibling, but rather they're uncle, niece, or something like this. And well, so how do I identify that that's valid? And the problem is that there's not a unique clique tree that I can define for my graph. There's actually, I think, something like 8 clique trees that I can make for this graph. And maybe I could have got lucky. I might have had this one instead, which would be red and blue are sibling, or I might have had this one, red and blue are parent, child, but bad luck. And, you know, thankfully, for the sake of my example, I got the wrong one. And so I didn't know which one to merge. So we don't do it this way. Instead, what we use is something called the clique graph. And the clique graph you can think of as being the union of all possible clique trees. So it's very slightly harder to compute. You can still compute it really fast. But it shows you all the possible connections that appear in all possible clique trees. And you get something that looks like this. And it happens to be the case that for my example, every single clique is connected somehow or another in some tree or another to every other one. But that's not always the case. It's just a sort of effect of the small size of the example. So there's definitely clique graphs where not everything is connected to everything else. And so now what should I do? So I can look at every possible merge. Anything that's connected here would be an allowable merge, which wouldn't mess up the chordal property of my graph. And I make an estimate of how much it would cost me to factor each of the two matrices separately, or to factor one matrix merged together. So I'm going to compute these edge weights, and the edge weight for the combination of two cliques is just the cube of the size of the two cliques, because I think that merging is a cubic operation, minus the cube of the union of the two things. And so this is how much it would cost me to factor it if I merged it. This is how much it would cost me combined to factor the two things separately. And if this is a positive number, then that means it's probably a good idea to merge them. So what we do is we compute the clique graph, we compute this metric for every edge, and we take the biggest number, that seems like the most advantageous merge. As long as it's positive, we merge them together. So we do that. And now what's happened is I have this reduced clique graph. I have filled in the off diagonals with values, with chords. And it turns out now that this metric would be negative on every term, so I would stop. And it's worth saying that when I fill in these numbers, what I'm doing is I'm filling in a structural non-zero. I'm saying that for the purposes of decomposition, that term must be 0. But for the purposes of decomposition, each of the blocks that composes it could be some non-zero number, as long as they eventually add up to 0 to give me the whole graph back. And I do this over and over again. Okay, so that's what we implemented for STPs. And now what I want to show you is free software for semi-definite programs. So, or actually not even semi-definite programs, but just general cone programs. So we started working on this, I guess about 3 or 4 years ago. And the idea was to, like with OSQP, make a completely free, open source, general cone solver that would work for STPs, QPs, second order cone programs, exponential cones, all of these things. So a much more general version than OSQP. And we released that as a Julia project. So you can just, if you use Julia, which I would definitely suggest that you try because it's really, really good, you can download this package called Cosmo, and you go to our website and you get lots of software and examples and benchmarks and so on. And it implements this chordal decomposition method that I described. but it also implements loads of other stuff that I haven't said anything about. So we have a lot of stuff in there about infeasibility detection. It's not completely clear how you should detect when a problem is infeasible using these ADMM-based methods, but we have a nice solution for doing that. It does chordal decomposition. It does the clique merging. We do things like custom cone definitions. So if you know something special about your cone, you can bake that into the solver and make it run faster. You can exploit structure in A and P if you want to have, say, a special solver for a predictive control problem. If you want to solve on a GPU, if you want to do indirect linear solves, all of that stuff is in there. And like OSQP, it's free and open source with Apache 2.0 license. Okay, so and one final thing to say is that our experience with this is that Julia was a really nice language to develop in, because it took us a long time to get OSQP, the kind of the QP version of this package, to work. Getting a basic Julia version of the same thing was really fast. And the performance is about the same. The numerical performance of solving just a QP in Cosmo, you get almost exactly the same computation time as if you did it directly in C. And that's true for problems at all scales other than like the very smallest problem. If your problem has 4 variables, the C version is probably going to be a little bit faster, but that's mostly just the overhead of the extra machinery in here for more complicated problems. Okay, so I encourage you to try that if you want. I should always show some numerical results for any solver. So here's my obligatory table of numerical results. And what we did was, because I want to show you the effectiveness of the clique decomposition, we just made a kind of toy problem here where we could scale the size of the problem by either defining more and more of these little blocks on a constraint with this arrowhead format, or make the blocks bigger and bigger. And then we just tried it for all different problem sizes. So here we go, increasing the number of cliques. Here we go, increasing the size of the cliques. And this column is our solver with chordal decomposition, this one without chordal decomposition, this one's Mosaic, and then SCS is a first order solver, which is using basically the same method as us, but with no chordal decomposition. And it's really amazing how much of a speed up you get when you do this chordal decomposition and clique merging. So for the biggest size problems, something that takes you 5 minutes in Mosaic, you can do in 7 seconds. And likewise, for different size cliques, you start to get these really huge computation times because factoring a big matrix is expensive, whereas we kind of top out at about 30 seconds. Okay, so there's many other results that I could show you. I'm not going to do that. Rather, I'm going to thank you all for listening to the talk. This is not the last slide, I think. There should be one more. But if you want to go and try out any of these things, you can go to our website. It's all on GitHub, and you can download it and try it. And then I say one final thing, which is that I said that our solvers are good for really small or really big problems, but not so much in between. And so we've been working on the in-between case and trying to make an interior point solver that gets the same kind of open source treatment. And so we have one, it's called Clarabelle.jl, and it's a generic interior point method for cone programs. It should solve SOCPs, QPs, LPs, and so on. It's quite a bit faster than other options that you would have, like ECOS, say. And we're going to release that probably by July at the JUMP conference that's coming up in July. And we're also working on an embedded version of this. So you should be able, not in Julia, but in Rust. So you should be able to deploy an interior point solver onto an embedded system using the sort of Rust counterpart of this package. Hopefully by October when my sabbatical ends, otherwise it's going to be really slow. So thanks very much for listening to the talk, and I'm happy to answer any questions.
Thank you, Paul, for the very interesting talk, and I would open the floor for questions. Anyone from the audience, you can type your questions in the Q&A tab. If there's no question yet, I would ask the first one, Paul. Yep. It appears that these decompositions should also work if you would approach non-convex problems and want to compute decompositions for non-convex problems, or do you see there a major bottleneck why it wouldn't work in the non-convex?
Well, so the decomposition that I described there is really one for decomposing a sparse semi-definite cone, and it's really based on that Agler's theorem tells you that the semi-definiteness of a bunch of small pieces implies if and only if the semi-definiteness of a big matrix. So it's not a generic procedure for just taking a sort of big problem and breaking it up into small pieces, but it's kind of focused specifically on that one constraint class.
Okay, thanks. Are there further questions? Boris?
Yeah, maybe if I may ask one question. So I was wondering if I want to compute the maximum eigenvalue of, say, a large sparse matrix that is symmetric. I could formulate that obviously as an SDP, but I was wondering what's faster now, using Cosmo with this clique merging, or would it be faster to directly use an existing linear algebra tool to compute the maximum eigenvalue?
Just guessing, I think that it would probably be faster, like a lot faster, not to solve it as a semi-definite program. Because if you're trying to just compute the maximum eigenvalue of a matrix, then you have all kinds of like Lanczos method or power method type options, particularly because you only want one. That would certainly be much faster, I think.
All right. Yeah.
And in fact, I mean, I didn't say much about it there, but one of the other things that we've worked on is using kind of approximate projection methods to nearly get the projection onto the semi-definite cone. So not just break it up into small pieces, but then just kind of make an approximate projection. And those are based on basically the same method as you would use to get the maximum eigenvalue in the first place.
Yeah. I see.
Okay, and we have a question in the Q&A coming from Ying Zhao. Thanks for the talk, really interesting. You mentioned that the SCS is similar to your solver. As far as I know, SCS works with the self-dual embedding which simplify the complementarity condition. What is the link between SCS and the Cosmos?
Okay, so right. So the difference is that, so when I say it uses the same method, what I mean is that it uses ADMM. But it uses an ADMM on a different problem formulation. And what happens in SCS is exactly what the person said in the question. They write down the self-dual embedding. So you get a problem which is the dual of itself. And then you solve. And so you don't have to, in that case, worry about infeasibility detection, because the self-dual embedding always gives you an answer. And then you look at the answer and then you decide, does the answer tell me that the problem is solved, or does the answer tell me that the problem is infeasible? But either way, you can extract the answer to the question by looking at the solution of this embedding. So we don't do that. Instead, we detect infeasibility by looking at the difference between steps, which I think is not as good a way of doing it. But the upside of our method is that we have been able to keep this quadratic term in the objective. We've been able to keep that quadratic term in the objective. Whereas in the self-dual embedding approach, what you have to do is you have to upper bound the quadratic term with some linear term, which makes a second order cone constraint for you. And then you solve that problem, because the self-dual embedding does not work if you have a nonlinear cost. And our experience is that if you have a quadratic term, particularly in a QP, and you can keep the strong convexity in the objective, then it solves much faster than if you were to take it out and embed it in a second order cone constraint. And I know that in SCS, they have a method for dealing with this, for somehow keeping the quadratic term in there and doing still self-dual embedding, but I'm not sure if that's made it into the sort of mainline version of their solver yet.
Thank you, Paul, for this extensive answer. And there is yet another follow-up from Ying Zhao. And he asks, or he comments on that SCS is really sensitive to the conditioning, or not well behaved in really large scale problems when dealing with semi-definite constraints. How do you solve this issue in Cosmo?
Well, we have about as much success with it as they do, probably. I mean, so we, if the problem is badly scaled, then what we do is we, that linear system that I said we want to solve at every iteration, we do some scaling to that. We do something called Ruiz equilibration. I think that's exactly the same thing as they do in SCS. And I mean, basically the problem is it's a first order method, and if your data is extremely badly scaled, then it's just not going to work. So you have to have at least a reasonable problem. The scaling does save you to some extent, but it can't completely save a dreadful problem. And for really huge STPs, yeah, it's a problem. I mean, if you have a really badly conditioned gigantic STP, then they're just hard to solve. We did a lot of stuff in Cosmo for using acceleration methods, Anderson acceleration and methods like this, which help a bit. But I think it's still kind of an open question how you do first order optimization with really badly scaled data.
Absolutely agreed. Thank you. It looks like there are no further questions coming in, so I would like to thank all the speakers for the interesting talks, and can also already give you and the audience a heads up, because on the 27th of June, we will have the second part of this seminar. Again, same title, Trends on Software for Optimal and Predictive Control, 27th of June, and we will publish the list of speakers in due course. And with this, Tulasi, do you have final words for us to close?
Yeah, just I want to echo what Tim said. Thank you very much for all of you who joined us, and thank you very much to our three speakers. It was, for me, very, very interesting. And also you can see here that we have the second part of this coming up, as Tim said. So if you have any feedback on today or on ideas for the next seminars that we plan to organize a few of these every year, just please email either Tim or myself. But yeah, to close again, I want to thank again all of you. So Boris, Gionata, and Paul in particular, it's been very, very interesting for us. Thank you.
Thank you.